and beats. In this video, we are going to go ahead and extend the already established power rule so that it also works for negative integer exponents. And we're going to do this by using the recently established quotient rule for derivatives. Let's get going here. All right, so what do we already establish? Right here, here's the power rule that we've already determined, and that is the derivative with respect to x of a power function x to the n is equal to n times x to the n minus 1, and that was under the assumption that the exponent n there was a non-negative integer, so otherwise known as a natural number or 0. We already figured this out. So what we'd like to do is show that this is also true when n is a negative integer. So that's what we're saying here. That's what I was saying earlier, is that we're going to use the quotient rule to establish the power rule to be extended for all integers. All right. So to do this, what we're going to do is just say, look, let's call m equal to negative n so that m is positive, which would also tell us that n is negative because it's negative n. So for m to be positive, negative, negative, n gives us a positive, hence n is negative. All right, so we're just going to call m negative n here. Then, if we go ahead and investigate the derivative with respect to x of x to the n, well, because we're calling n negative m, or equivalently m equal to negative n, then the derivative of x to the n with respect to x is going to be the derivative of x to the negative m right here with respect to x. But also remember, we're assuming m to be positive, hence that is the same as the derivative with respect to x of 1 divided by x to the m right there. So you notice that is a quotient, 1 divided by x to the m, where m is assumed to be positive. So we will apply the quotient rule, and let's see what we get. Quotient rule tells us, all right, take the denominator function, multiply it with the derivative of the numerator function, so that's x to the m times the derivative of 1 with respect to x, minus the numerator function 1 times the derivative of the denominator x to the m with respect to x, all divided by that denominator x to the m quantity squared. Now, when we differentiate 1, right there, that just leaves us with 0 times x to the m, so that's where we get this 0 right there. And then the derivative of x to the m, power rule, is a m times x to the m minus 1, because m is assumed to be positive. Hence, we get 0 minus mx to the m minus 1 in the numerator. And in the denominator, x to the m squared, properties of exponents tells us that's x to the 2m, right down there. And thus, this is the same as negative m to the x to the negative m times x to the m minus 1 divided by x to the 2m. And if you simplify that, that's the same as the constant negative m times x to the m minus 1 minus a 2m, just again using properties of exponents, which is the same as negative m times x to the negative m minus 1 once we combine the m minus the 2m in the exponent there. Now, in terms of n, now, remember, m was equal to negative n. So, we will replace the negative m's in our expressions with n's, and we see that negative m times x to the negative m minus 1 is the same as n times x to the n minus 1. And what we have just shown now is that, oh, indeed, if n is negative, then the power rule is still the same rule that we had previously established. And we were able to do this because we have now established the quotient rule for derivatives. Thus, conclusion is that the extended power rule right here, the derivative with respect to x of x to the n, is n times x to the n minus 1. And now that is true for all integer values of n. So remember z here, that symbol just represents the set of integers, positive and negative whole numbers, including 0. So it's true for all integers now. So that's nice, because now we're going to look at an example of how to use this. So we're going to find a couple of derivatives here using the extended power rule that we just came up with to establish some derivatives. So in part A here, notice we're trying to find the derivative with respect to x of the function 11 divided by x to the 7th. Now at first, one might be tempted to use the quotient rule, which of course there's nothing incorrect with doing that. However, the quotient rule, as we have seen, involves a variety of steps, right? We have the quotient rule where there's a denominator being squared and a difference of derivatives times other functions in the numerator. So if we could avoid the quotient rule, then we should, maybe that will help us if there's an easier route. And so that's the kind of the point of this, is that, all right, I could use the quotient rule here, but now I just showed that the power rule is true for negative whole number exponents, and thus I can just rewrite this derivative as the derivative with respect to x of 11 times x to the negative 7th, right? And now I don't have to use the quotient rule at all. I just use our power rule that we just established. So what do we get? 11 times, bring down the exponent, negative 7, times x to the negative 7, and then minus 1. And thus the derivative is a negative 77 x to the negative 8th, or if you prefer, a negative 77 over x to the 8th. And there you have it. It's just the extended power rule now. Let's do one more. How about this derivative that we're trying to find? The derivative with respect to t of the quotient 4t to the 15th minus 7 divided by t to the 6th. So again, you could use quotient rule here, but rather something to keep in mind moving forward is, can we simplify the function that we're trying to differentiate prior to differentiating? And in this case we can, just noting that of course here t should be non-zero, because of course that function is not even defined when t is 0. And if we simplify this function, we get d dt of, well, 4 times t to the 15th minus the 6, just using properties of exponents, minus 7 times t to the negative 6, right? Because essentially that right there, that function, is the same as 4t to the 15th over t to the 6th minus 7 over t to the 6th power. So I just split it up into individual terms, and then I'm going to apply my properties of exponents to get that this is the same as the derivative with respect to t of 4t to the 9th power here minus a 7t to the negative 6th power. And now we can see we can just differentiate term by term using our extended power rule, which gives us, well, let's do it. Let's do the power rule. 4 times 9 times t to the 8th for the first term, and then minus a 7 times a negative 6 t to the negative 7th power, right? Power rule, power rule. And so what do we get? A 36t to the 8th, and then plus a 42t to the negative 7th. Again, if you prefer, 36t to the 8th plus a 42 over t to the 7th. Sometimes it's nice just to write our exponents as positive in the end, but it is not completely necessary. This step right there is totally acceptable. And there you have it. We just showed that the power rule can be extended to negative integer exponents as well. And we looked at a couple of examples, and that's really the end of this video. So next video, we're going to look at derivatives of powers of the natural exponential function. And then after that, we're going to move on to derivatives of trigonometric functions. So that is it for this video. Until next time, it's Math and Beats, and I'm out of here.